Hello and welcome. In this lecture, we are going to be sorting out the angle of our blend space, hooking that up to our gameplay, and in the process, we're going to have to learn a lot of maths, a lot of transforms and vectors. So let's dive in and figure out how that works. Okay, so we want to be able to get the angle at which we should be moving. However, before we do that, we need to do a little bit of maths because we want to understand how we can get this angle which is local to the player, and I'll explain what I mean by local and global, and how we can get that from a global velocity and what those terms mean anyway. So let's have a look. First of all, we need to have a bit of a basic primer on transforms and what transforms are. We've seen them, or you have seen them a little bit before when you look at any of the scene components, that's these ones in the hierarchy. You can see they have a transform here. It's the location, rotation, and scale properties. That's basically what a transform is. But one thing that you're not seeing here is that also part of this transform is the fact that these scene components are in a hierarchy, meaning that the transform also has a parent, or, they're basically hierarchical. So how does that work? Well, here's a kind of toy example. We've got the cube here, which say is our base. It's the center of our world or something. So that's going to be our world space. We've got this character here, the little smiley face, and he's got a position in the world relative to his home base. And then this character has a gun, and the gun has a position relative to the character. So the way this hierarchy works is that the parent of the gun is the parent of the character is his home base or the world. And then we have some local coordinate systems within these. So the world's coordinate system is the world system, the global system. Then the coordinates of our character are then local to its position. So the gun is positioned relative to its character. What does that mean? That means that if the character decides to go off on a little escapade, then the gun moves with it, because the position of the gun relative to the character has remained the same, but because the character's moved, its position in the world has moved. Same happens with rotation. If the character turns around, the gun must turn around as well. That's how transforms work, essentially. There's also scale, but we're not going to look at scale. It's the same, but it's just complicating things, and we don't need to have a look at that. It's not relevant to us. So let's have a different look at this. We've got global space and local space. So the global space has the base at the center of the world, and the character has gone off and to the right. The local space, on the other hand, sees things in the opposite light. It says that the character is the center of the world, and that the base has gone over to the left, has gone backwards. That's the difference between global and local. It all depends on your point of view. Everything is relative. So this is what we mean when we talk about transforming between global and local space. And which one are we interested in? For our angle, we're interested in a local angle relative to where the player is looking. We're saying, are we moving over to the right? That's what we're saying, that not globally, but locally. Are we moving to the right locally to our player? Because if our player's turned around 180 degrees, he shouldn't play a left animation just because he turned around. So one more important distinction is how we do transformations for vectors of different sorts. The first example I want to look at is a position vector. So a position vector basically is a vector that gives us the difference between the current location, or the 0 point in our coordinate system, which when we are focused on the character is the character himself, and then it gives us an arrow that points to where something should be. So in this case, it is the gun location vector. Now, if we transform this into our world space, this is what happens. The arrow now points from the center of our new world, the global space, and it points to the gun. So that's what happens if you transform a position vector. Now, if you do a direction vector, things look a little bit different. A direction vector is one that says, this is the way I should point, not necessarily where a thing is. And this transforms rather differently because we now aren't interested in it pointing to the same location. So that position doesn't really get updated. Instead, the vector gets rotated and scaled or whatever it is, and we end up with it looking a little bit like this. So that's actually the kind of transformation that we want to be doing, because we're dealing with a velocity, which is a direction vector rather than a position vector. A velocity doesn't tell us anything about where we should be. It tells us about what direction we should be going in and how fast we should be going in that direction. So with that theory out of the way, let's go ahead and calculate our direction from this velocity. So we know that velocity is in global space, and we want to convert it to local space. Now, that means that, generally speaking, we're always trying to do things the other way around, usually, because we're saying, well, we've got the position, the local position of a gun, its local transform. We want to figure out what it is in world space so that we can render it relative to everything else. Now, that's not what we're trying to do here. We're trying to do the opposite. So what we actually want is called an inverse transform. The transform goes this way from local to global. The inverse transform goes from global to local. So because we've got this global velocity, we want to inverse transform. So let's take off here and look for inverse transform. And you can see that we've got these two options. We don't care about these matrix ones. We've got the two options for direction and location. And as I said, the difference is that a location will move that position around. The direction is just going to apply the rotation and scale. So we want the direction. We need a transform to rotate it by. We're going to have to get that transform of the pawn itself, of the character. Where is that pawn in the world? So let's go ahead and grab off the pawn owner and look for the transform property, get actor transform, that would be the one. We'll pipe that into our inverse transform direction, and we've got ourselves a new vector out of this. So the next step would be to get the rotation of this vector. So we're going to look for rotation, see what we can find. We've got find look rotation, make rotation from axes to quaternion. No, let's have a look at rotation from X vector. If you read the documentation here, it says it's going to set the yaw and pitch from this vector, but it won't set the roll because it can't get that information from a vector. That's fine. We don't care about the roll. In this case, all we care about is the yaw because we want to see how far we're turning to the right or left. So rotation from X vector, that's the one that we want. It's going to return us a rotator. And for us to get just the yaw from that rotator, we're going to right-click on the pin and hit split struct pin, which goes ahead and splits that struct into the roll, pitch, and yaw. You could do that on a vector as well, by the way, I think. You can right-click and let's see. I think I'd have to break the link to do it, so I'm not going to show you. But basically, we've now got our yaw here, and that's what we want to set. So again, mini challenge. Set up the yaw to be the angle and test it out. So again, mini challenge, set up the yaw to be our angle variable that goes into the blend space and test it out. Try it out in the game and see if you're able to run around successfully. Okay, welcome back. So we're going to drag in again our angle variable, set angle. Going to set the angle from the yaw, and we're going to get the execution pin from the end of speed. Going to compile and save that, and we're going to go over to the sandbox and hit play. And now let's try moving around. A controller would be ideal so you can test out the different gradients and the nuances. And sure enough, you can see if I start moving around now, I'm able to move backwards, I'm able to move forwards, sprinting, and sideways, and 45 degrees. All of that works based on the maths that we've calculated to calculate our angle. Great stuff. So we've learned a lot about transforms and vectors and how you can transform vectors, both inverse and forward transforming. And in the next lecture, we're going to look at fixing this foot sliding that we are seeing here. I'll see you there.